scientific community and then also in the enterprise. However, the learning curve for those distributed frameworks is quite steep, and hence they could not be very popular. Whereas Hadoop had made a lot of things simpler, and it's easy to use, easy to learn, and also solves some of the problems very elegantly. Hence, Hadoop became very popular. So how did the whole thing about Hadoop started? So if you look at the screen, can all of you see the screen?
Yeah.
Okay, so this is the famous paper from Google. It's a research paper. It is written by Jeff Dean and Sanjay Gehmawat. Both were PhDs, I believe, working for Google. And the success of Google and the PageRank algorithm is directly due to this paper. Okay, so in this paper they discuss about the MapReduce programming model. What is a MapReduce? How is it being used?
Hi, Reddy.
Hi.
Ready? Yeah,
Yeah.
hi, this is Shruti. I've just arrived because of network problem. Could you please tell me in like quickly what all you have covered till now?
Okay, sure. So we just started. We didn't cover much. So I was just saying them that distributed computing is the key for the future for big data analytics, right? These why Hadoop became so popular, because it solves some of the problems elegantly compared to other frameworks. Other frameworks have been used by the scientific community, especially in the astronomy world, where there is lots of data related to stars, pulsars, planets, the galaxies and things like that. They use lots of distributed computing. They have their own frameworks, but they were very limited and used by specific communities. There was another toolkit called Globus Toolkit. I was thinking 10 years ago that is the framework that is going to get famous. For some reason, they overcomplicated the design of the Globus Toolkit. It is completely based on SOAP web services, and to write a client or to write some program, it was not easy. You have to do several things in order to get to writing a small distributed program. So then came in 2004 this paper from Google. Two guys, Jeff Dean and Sanjay Gehmawat. These guys are excellent guys. Jeff Dean especially is supposed to have a very good IQ. They have, and one of these guys, I think Jeff Dean, I believe, has built Gmail over a weekend. So these are the kind of guys that have written this paper. They introduced the concept called MapReduce programming model. And this is the concept that has taken Google to the new heights, so that they can search the web and index the web very effectively, and then apply some algorithms on the top of the MapReduce programming model to serve their web community. So we'll discuss about this paper today. It's important to understand the roots where the MapReduce have come, and I want to make sure that you understand MapReduce thoroughly, because Hadoop implements, it's an open source implementation of this paper. Google's implementation is not available on the web. It is private and they keep it to themselves. Whereas Yahoo started work on this sometime in 2004, and then they released the Hadoop to open source in about 2007-2008 timeframe. And then since then, Hadoop is being adopted by many organizations, and over a period of time, Hadoop has become very popular. Lots of tools, lots of algorithms have been developed around Hadoop. There is now a lot of significant user community, and in fact, it's interesting to see that by open sourcing Hadoop, Yahoo has spin off a new economy itself in terms of, at least there are 5 to 6 companies that are breeding on Hadoop technology, distributing Hadoop. And there are several people, consultants, big data architects, lots of enterprises working on Hadoop to solve their enterprise problems. So it has created just one paper and a piece of open source technology has really changed the world of big data analytics. Okay, so given that background and given this MapReduce paper, let's discuss this paper a little bit more detail. So again, we are going to touch this MapReduce in the next few classes thoroughly and in depth. Hello. Hello, can all of you see my slides? Can someone respond?
Yes.
Yes.
We can see the slides.
Okay. So when I ask a question, please respond so that, since we are doing this online training, with 7 oceans apart, right? So we need some collaboration and communication so that we can close. We can be more affinity, there will be more affinity if you answer the questions. Okay. So because when I open the slides, I don't know whether you're looking at it or not. So please be active, and because I think it's good if you can ask some questions. Okay. All right. So I'm going to the next slide. So we've discussed Hadoop and why Hadoop is required. So Google has this requirement. So again, we are discussing Google paper. The context is Google paper. We're not discussing the whole world about Hadoop right now. So we'll keep Hadoop in the background, and we're discussing the rationale behind this paper. We're discussing how they wrote about this paper, how they started using MapReduce. So Google had this huge requirement in terms of large computations and huge amount of data sets. The data sets are huge, really huge, 400 terabytes of data, right? If you were to copy the data into disks, index them, it is going to take lots of time. So they need hundreds and hundreds of special purpose computation. They also have hundreds of special purpose computations. They want to find out which website is very famous, which link is being accessed, which products are being accessed, right? So that they can create an economy around such. They've created essentially a huge economy around such. They're very successful because of such. So if I send an email to myself saying, I'm looking for a camera, then Google will actually, you will be surprised to see that Google will on the right hand side will show some advertisements related to cameras. Just imagine every day there will be millions of messages being sent. Immediately when I send a message, and I can see ads on the right hand side related to the message that I've sent. So they're doing contextual advertising. So how are they doing it? I mean, they have probably more than 20,000 computers in a cluster. They are like spies. Once the message comes in, they're very actively looking to index the document and then find the related content, advertisement content. How do they find it? How do they know that I'm looking for camera, right? They look at most frequently used terms on particular category. They use lots of natural language processing. They use lots of semantic search. They use a lot of searching within the text that I have sent in terms of the Gmail, and then serve their ads on the right hand side. So in these computations, right, obviously this process that they're writing obviously has to process huge amount of emails, huge amount of Twitter messages, huge amount of Facebook messages, huge amount of Google Plus messages, huge amount of Outlook messages, right? And again, so this kind of computations require lots of coordination in a distributed framework. They analyze, they have to crawl the documents. These computations, they have to write these computations to crawl. When you say crawl, it means that you open a website and you look and everything and anything inside a website. If there are links that are there inside the website, go to that links till all the links are finished. Read in every line, every word of the HTML page. In fact, you would see they are also indexing PDFs, Word documents, PPTs, whatnot. They're also doing image searches. They're now coordinating image and text searches, right? So all this is possible through some of the innovation that has happened through this paper. They want to look at the web request log, right? One person, if he visits 10 websites, just imagine that 500 million people visiting multiple websites. They want to look at all the web request logs. So this is a huge computation problem. It's not an easy problem. It's very easy in terms of the requirement, right? But in terms of handling the data, in terms of the computation requirements, it's a very complex problem. So these are some of the things that they compute. Inverted indices. Inverted indices, I will tell you, it's not it's not a big term. It's a very simple term. So if you buy any book, right? If you buy any book, you will see index on the back side. That is called inverted index. That's as simple as that. So instead of going through the whole document and finding out where the word is, we invert. We go back to the document, back to the index, the backside pages of the book, and then go back into the book and find out where that word and which page that word is working. Similarly, all the web pages across the world are inverted indexed. So if I search for Reddy Raja, so Google knows that somebody is looking for this, and it exactly knows in how many documents, in what websites Reddy Raja is already there. So they will immediately pull up those documents, check those links, and then present you in a nice search output. Then there are various representation of graph structure of web documents, especially the LinkedIn. Right, there is also a knowledge graph. If you now type Sachin Tendulkar, you will see all his records on the right hand side. How many runs? I didn't ask for the information on Sachin Tendulkar. I asked only Sachin Tendulkar, the search page, but it gave me when he is born on the right hand side information about Sachin Tendulkar. So this is called knowledge graph structure. They are trying to create graphs of knowledge related to Sachin Tendulkar and all the web pages related to Sachin Tendulkar. Right, and yeah, so there are so many things like that. Again, because it is data, there's so much of data. You won't know what kind of insights you can get in, right? You won't know. It's not. It all depends on how you can analyze the data, how you can interpret the data, how you can cross correlate the data, and how much capacity you have got to write computation programs on the top of this data. right? And these are the general problems that they faced, right? Computations are straightforward, but input data is very huge. Computations have to be distributed across hundreds and thousands of machines in order to finish in a reasonable amount of time. So if I send an email, immediately ads come in, right? So that means that computations have to be distributed across hundreds and thousands of machines in order to finish in reasonable amount of time. See, out of these hundreds and thousands of machines, lots of coordination has to be there. Which machine actually takes my Gmail and then indexes it and goes to advertisement in repository and fetches the correct advertisements, right? Which machine does that? How is it being collaborated? Because out of 100,000 machines, the task has to be assigned to one machine. Once assigned, we don't want to assign the same thing to other machines, right? So again, what if a machine that is assigned fails? So these are the kinds of things that they wanted to deal. So the big issues were three. There are big issues. They want to parallelize the computation, and they want to distribute the data, and it requires to write large complex code to deal with these issues. So in the first class, we kind of touched upon some of these topics, and again these issues are mentioned in Google paper. So the major challenges are how to parallelize the computation, how to make sure that the data is distributed so that the programs can run on the data, how to write Claude. So then, in order to do this, in order to solve this, they have to write a large complex framework, a large complex code to deal with these issues. As I said, as we discussed in the last paper, last discussion in the last class, writing distributed framework is hard. There are a lot of challenges there. So that's what they're saying. So then they came up with a mechanism, right? Then they said, okay, let us write some requirements. What is the motivation for large scale data processing? Let's take a cut at it and see how we can manage this. So then they said they want a runtime system that takes care of the following. They want a runtime system that takes care of the following. So they want to partition the input data, right? So the whole 400 terabytes of data, they want to partition it. They don't want to treat the data as one whole set, but they want to partition it. They want to schedule the program execution across set of machines, right? So that if there is a hard big problem, then the program can run on multiple machines on multiple input data sets and then gets the result. And then the other biggest problem is handling machine failure. So it is hard. I mean, if machine fails and we don't know out of 100,000 machines, the IT administrator doesn't know which machine failed. Or no, it's a huge data center with lots of blades. How to detect a machine failure and make sure that that machine is repaired or replaced and things like that. What happens to data inside that machine? What happens to the task that is being run on that machine as of now when it fails? So those are the things that they have to deal in large scale data processing. They also have to manage a bigger problem, that is inter-machine communication, right? Inter-machine communication. The inter-machine communication is very important because if there are only two machines, they can talk to each other nicely. If there are three machines, you can still handle them. There are hundreds of machines, thousands of machines, 100,000 machines in a cluster. All of them have to communicate with each other and coordinate with each other. So there has to be a protocol in terms of sending and receiving messages. There has to be a method. It is possible that suddenly these 100,000 machines talk to each other and there can be a chaos. The whole network can get jammed. So it is important that the inter-machine communication is built with some standards, with some protocols, with some rules. So they cannot just talk or they cannot just send messages like that. Each machine has to follow certain protocols. Each machine has certain duties. Each machine has certain responsibilities. Right? So those are the things that they have to design in order to come up with a huge framework. Okay, so you folks are following me? Hello? Hello?
Yes, we are following you.
Yes, yes, sir.
Okay, good.
Yeah, yes.
Yes.
All right, good. Thank you. So then what is the benefit if these kind of issues are being addressed by the framework? What is the benefit to the programmers? Benefit to the business analyst? Benefit to the IT infrastructure team? Benefit to the CIOs? Benefit to the CEOs, right? CEOs, they want to save money. Whereas for programmers, for example, if you give a programmer, okay, I'm giving you 100 years of weather data, go and find out which year, what month, which day was the hottest and similarly the coldest. So if you give this problem to the programmer, he will get puzzled. Oh my god, there is 100 years of data, right? The biggest thing is how do I manage this data? Where is the data in the first place? How much time it is going to take me to look at this 100 years of data? There is data, every day's data is there, every hour's data, weather data is there. So if you ask TCS to build answer to this program, they will say, give me $500,000, right? Because they are going to take 3 to 6 months to get an answer. Sorry, I'm not using TCS. I'm just saying that problem is hard. I'm not undermining TCS here. I like TCS. The problem is hard. But with this framework, with Hadoop, and if data is there in one of the distributed file system, and if you have 30,000 machines in the cluster, with Google MapReduce model, I can get the answer in 5 minutes. That is the power of the MapReducing model, MapReducing paradigm. I hope you understand the model now, right? That is where the value of Hadoop is coming. That is where the value of large computations. That is how the enterprises want to unearth. That is how the enterprises want to mine their old data. They want to understand the patterns in their old data, right? So that is how they want to do it. That is why Hadoop is becoming famous. So the biggest benefit for programmers is, without much experience, they can write parallel and distributed systems to utilize the resources of a large distributed system. Now in the few classes subsequent classes that we discuss, even administrators like us who does not have much experience in Hadoop or distributed framework, we would be able to analyze some data sets with hands-on tutorials with very simple SQL-like queries, and then get to some insights into the data set. So we'll have two hands-on with some of the tools around the Hadoop. We'll be able to analyze some data as administrators, and then get or understand the beauty and the power of the platform. So this is how Google has tried to implement the MapReduce model. Google implementation takes, it runs on large cluster of machines. So in fact, it is required now. Not one machine can solve the problem. We require large cluster of machines. It has to be highly scalable. Highly scalable means that as the demand grows, as the size of the data grows, you can keep just adding machines. You can keep adding machines, and the system or the cluster have to scale. There are two terms here as administrators I would like you to understand. Scalability comes in two forms: vertical scalability, horizontal scalability. Do some of you know? Can some of you tell me the difference between vertical and horizontal scalability? Okay, so it's very simple. If you have a small plot and you want to build a small one bedroom house on ground floor, after some time your requirements are not met, you will build another floor. That is also not met. You will build 7 floors. That is also not met. You will build 30 floors. That is also not met. You will build 110 floors. That is vertical scalability. Use the existing machine, upgrade the motherboard, upgrade the memory, upgrade the CPUs, upgrade the hard disk. Try to keep on doing upgrading. That is vertical scalability. You understand? You understand now what is vertical scalability? Hello? Yes?
Yes. Yes.
Yes. Okay, good.
Yes.
This is a very important term. You have to understand these two. Horizontal scalability means build another building next door, build another ground floor. That's it. Keep building more houses next to each other. So don't try to build apartments on the same plot. Build houses next to each other. So that is horizontal scalability. Right? So which means adding more machines to the cluster. Add similar machines, same capacity. Keep adding. That is horizontal scalability. Now you understand. There are issues with vertical scalability. So if there is a problem in 6th floor in terms of a pillar, what happens to the apartment building? What happens in vertical scalability? If there is a problem with one of the component in a machine, the whole machine becomes useless. The whole apartment complex becomes useless if there are structural problems. Whereas with horizontal scalability, even if 20% of the machines fail, 80% of the machines are still in use. That is the concept that Google took forward for highly scalable clustered system. Okay, so you have to understand this as an administrator. And they say that all these machines that are part of the cluster are commodity machines. When I say commodity, they are cheap, not as cheap as laptops or the desktops that we buy, reliable machines, but definitely not $100,000 or $200,000. They could cost $5,000 a piece, something like that. Okay, you understand, right? That is the motivation, that is the requirement, that is how they started designing. So this large scale data processing had to take terabytes of information on thousands of machines. So again, I don't know if you're feeling that it is too theoretical. It's very important to understand the concepts. I hope you guys agree. Okay, and definitely we're going to get deeper and deeper, and you will be getting into the dirty business of managing Hadoop cluster, and you will see command line tutorials. You will see how to stop Hadoop. You will see how data is being pushed into a distributed file system, how you can do computation, and all that we're going to see. But the theory behind it is very important. The strategy, the design, right? So if you want to, if Prime Minister Manmohan Singh has to take care of the government, he needs a big picture, and he doesn't have to get into the details of it. So this is the theory behind, this is the big picture behind the MapReduce. So you understand this. So many then
Ready?
yes,
Ready?
yes,
Yeah,
go ahead.
I have this question.
Yeah.
Is there actually that we use? Is there anywhere that we use vertical scalability when it comes to real projects? Since this is one of the terms in scalability. I mean, this is one of the categories of scalability.
Right.
So is it somewhere that we use?
No, in Hadoop it is all horizontal scalability. Vertical scalability is used, but then it is going away. If you're looking at a massively parallel supercomputing from IBM Big Blue or big parallel computer from CDAC or Japan, that is kind of, you can closely related to vertical scalability, even though it is parallel computers, but everything is enclosed in one box. That is too risky. So even today, even for enterprises, even for mission critical applications, today, as we speak, people are preferring horizontal scalability. You might have come across terms like load balancer, terms like clustering, right? All these are in one way or the other related to horizontal scalability. One machine is too risky. Even in case of vertical scalability, they have redundant machines. For example, if you take any machine on Amazon.com, right? So either they have one more machine for every other machine, or one more application ready to be fired when the other application fails. That is too much of redundancy. With this kind of model, they don't have to have or manage the redundancy so much. Redundancy is inbuilt into the framework. So we will see that as we move forward. Does that answer your question, Shruti?
Thanks.
Okay. So the solution is they came up with a MapReduce model, right? So the MapReduce abstraction. What is this MapReduce? Everybody is talking about Hadoop, MapReduce. What is all this? So we'll get into the details. So it gets into it's basically very simple. It allows to express computations, but hides some of the problems. So it handles the messy details of how to parallelize a program, fault tolerance. So if machine fails, network fails, hard disk fails, how to recover from that? It handles data distribution, how data is distributed in a cluster. It handles load balancing in a cluster. Just because in a small team of 5 people, if 2 people are working very hard and intelligent, generally the manager dumps all the work to them. But in a cluster, it should not happen like that. Every machine in the cluster has to have some work, so there has to be a load balancing, right? So so I will give you a very simple example for MapReduce, and we will continue that in the next class until we completely understand the concept. Okay, so I will give you a very layman concept. So these are again, if you look at this, it talks about a word count example. It's not easy to understand word count example directly, so let me give you a simple example. So let's take a post office in New York, right? There's a post office in New York. All the mails from different places in New York come to one center. Okay, all the mails, letters that has to be posted across New York, across the country, comes to New York General Post Office, and it happens every day, 24 hours, 24/7. Right, the data keeps coming in, the letters keep coming in. Now let's assume that we don't have automated systems, we have manual systems for sorting out these letters based on zip code. So now obviously, let's say there are about 20 million letters that needs to be distributed, right, across the US. So they have to be grouped, categorized based on zip code, north, south, east, west, or state wise, or district wise, or region wise, some fashion, some category wise, they have to be grouped and then send it across, right? You understand the problem? So this is the problem that we're trying to solve. We're trying to solve or distribute 20 million letters with huge amount of people sorting these letters based on zip code, right? Now, how do we go about solving this problem? So if one person have to sort these 20 million letters, it will take a year for him, 2 years for him. So the post office decided to hire 100,000 people. So every person have to sort 100,000 letters. Then we can basically go about sending 100,000 emails every day, or 100,000 mails, physical mails every day. So that's why they decided they will hire 100,000 workers who will sort. Correct? That is the first problem. So now we are already getting it. So there's a huge data. We said we cannot obviously do with one single person. So we need 100,000 people, right? So we hired 100,000 people. Now, how do I how do I split the data? Right? This data comes in from multiple, multiple different small post offices across New York, right? All letters. So for example, a letter that comes from a small suburb in New York can either go to California, another letter can go to Texas, another letter may come to India, another letter can go to Seattle in the same bag that has come from a small suburb. So what should I do now? So tell me, what should I do? You guys have to answer. How do I assign these small sets of work to these people who are sorting? Hello? Can you hear me? All of you there? Yeah? Go ahead, depending upon. Yes, zip code is definitely, that's a very good idea. So now we need to look at the zip code of every letter, right? And then try to, but before even going to zip code, how do you assign work to these post office men, to this personnel? No, but the letters from the source can go to any number of destinations, right? So now we have this classic
We can
problem.
assign the work randomly.
Yeah, come again. Can you repeat?
We can assign the work randomly, and
Okay.
then after they sort that, they can just come together and again mix them up. Like suppose if a guy has 100 letters, so he'll sort according to the zip code, and he can then submit it to the main system according to the
Yes.
zip code.
Okay, pretty close. So that is exactly what the MapReduce model talks about. So you mix all the letters. You don't have to mix, but basically you take all the letters coming from all different places, put it in one room, and assign set of letters to each person, right? Each person. So this person opens, let's say, 10 bags every day, and then he opens each bag and takes a look at the zip code, right? Takes a look at the zip code, and then for every zip code there is a bin, there is a bucket, right? He marks with the zip code, there is a small bucket. So he sorts these letters using this zip code and separate them into buckets. Makes sense, right? So each bucket belongs to one zip code or set of zip codes. So let's assume for simplicity, each state in US is one bucket. All the zip codes corresponding to that state goes into that bucket, right? So now each of these person there are 48 states in America. So each of these person have 48 buckets. Like that, each of these 100,000 postmen has 48 buckets. So if you look at that, that means 48 buckets into 100,000 people. So you have 48,000 buckets. So now, surprisingly, all the letters are sorted into these buckets, correct? Now what is the next step? Now the letters are sorted into this bucket. What would be the next step?
We will
All the
store
similar
it into,
buckets should
according
be
to the zip code,
combined
we'll store
together
it.
so that they can reach to the same.
Exactly. So all these buckets have to be combined together so that we get one single bucket for every state, correct? So that is the answer. So now we have just discovered a pattern called MapReduce. So what we did, we took a huge amount of data, huge amount of letters, and we divided the task among the postmen, 100,000 people. That is called mapping. That is called mapping. That is called the map part of the mapping. Then what, when we combined and then try to merge and put into one single bucket for every state, that is called the reduce part of the mapping. Okay, so that is MapReduce model. So you understood by just looking at this model. It's called MapReduce model, and there are several explanations to this. So as a layman, if this is the best possible explanation. So that is how we understand the MapReduce model. So there are a lot of fundamental concepts here. We'll take this example for the next 2 classes, right? And try to understand Hadoop in terms of now how do they manage all this data. Okay, so let's say that a particular postman reported sick that day, right? So what happens to his set of letters, right? So then somebody has to take the responsibility of sorting his letters. Let's say a postman is too fast. One particular postman is too fast. So half the day he will be idling. Let's say a particular postman is very slow. Then I cannot finish my deadline. So by evening 6 o'clock, I have to sort all these letters and put on the flights. But if this particular postman is very slow and he cannot finish the work till midnight 10 o'clock, then the whole job is delayed till midnight 10 o'clock, right? So let's also say that these postmen needs a break in the middle. They go for lunch and tea, they come back and then do the work. So how do they coordinate? How do they coordinate all this work together, right? How do they distribute this data? How can we make this whole system fault tolerant? So these are the things that we would take this example and map physically to Hadoop framework, and we will map physically each of these roles and responsibilities of these people to physical process in Hadoop framework. Okay, so so I think that's all for today. I want to stop here. I want you to go back home and just digest this material. I will send this material, the paper. If you get time, read this paper. So we'll continue in the next class this paper and close this MapReduce programming model. Okay, so that you are thorough with the concept. And then in the subsequent classes, we take this example and then say, okay, each person is a task in Hadoop system. So who is that? What is the process? So there is a task tracker which is mapping this person's task to the computer, and the corresponding process is called as a task tracker, right? So now how do I store all the letters in the hard disk? So now in case of our example of Hadoop, instead of letters we have data, right? So how do I store all this data so that each of these people can access the data? So even if one postman is absent, some other postman should be able to access this data. So we need to design a distributed file system where each of them can access this data independently of the other. And at the same time, when it comes to reducing, when it comes to combining the buckets, we need to read data from different parts of this distributed system and combine. We need to read the data from multiple different buckets by multiple different tasks and then put it into a common place. So we need to access this file system, distributed file system, get these buckets from different places, from different computers, and then merge into one place. So we are going to use distributed file system. So how are we going to manage this data? Right? We don't want to skip any data. There may be, how do we deal with records or letters where there is no zip code? Things like that. So we will continue the class tomorrow, okay, with some of these concepts. Okay.
Yeah.
So I'll post these slides and the
Thank
paper
you.
to Kathy. So we'll continue. Okay. Thanks, guys. You guys have a good night. Bye.
Thank you.